This is G484 homework booklet question 23. So we've got a diagram of an aeroplane flying in a horizontal circle at a constant speed. The weight of the aeroplane is W and L is the lift force acting at right angles to the wind, as shown in the diagram. Explain how the force L maintains the aeroplane flying in a horizontal circle. I guess here, in general, this type of question I'd think of in terms of two possible answers: that the vertical component of L, so we can think of L as being split into a vertical and a horizontal component. The vertical component of L balances the weight, the horizontal component of L is towards the centre of the circle and therefore provides the centripetal force. More generally, I find it very useful to think of the idea of L plus W. So we could imagine drawing W there added on to L, and the L plus W gives me a resultant force there, which would be the centripetal force. But I think because the question was framed in terms of how the force L maintains it flying in a horizontal circle, it makes sense to give the component type answer. And really, we've got the horizontal circle, so the idea of a component providing the centripetal force, the circle, and then how come it's a horizontal force? In other words, how come there's no acceleration in the vertical plane? Because the vertical component balances the weight. Moving on. The aeroplane has got that mass, flying as a horizontal circle of that radius, and we're told the centripetal force acting on the aeroplane is that. Calculate the speed. Hopefully you think mass, you think radius, you think centripetal force. I can just use the centripetal force equation, F equals mv squared upon r, lob in the numbers that we know. There's the force. There's the there's the mass of the plane. There's the radius that we were given. Need to get that into meters, so 2000 or 2 times 10 to the 3, and then that leaves v squared. It's just a case of rearranging to get to two significant figures, 170 meters per second. Moving on to B, we're showing a satellite orbiting the Earth at a constant speed v. I'd just like to reassure you that that's V being lost against the D is my error and wasn't as it appeared on the original exam paper. And what's going on? We're asked to show the orbital period T of the satellite is given by that equation. Two things to say: it's show, so we've got to do the maths pretty formally, and this is a standard derivation that you're asked to make sure you know for the exam. So whenever we're dealing with satellites, whenever we're dealing with orbits, the starting point is to think in terms of, while the centripetal force, here we go, mv squared upon r, is equal to the gravitational force, gmm upon r squared. We don't need to worry about the negative sign there. The negative sign that is in the sort of official version of the equation is just symbolic of it being attractive. We need it to be attractive to provide that centripetal force, so we can just do that in terms of the sizes. Mv squared upon r is gmm upon r squared. As you can see, we get the little masses cancelling off. We've got the radius cancelling off the radius on the left hand side with one of the radiuses on the right hand side. That leaves us v squared is gm upon r, which I think was we used in one of the questions last week. This time then, the second step is to throw in that we need to use v is 2 pi r upon t. Remember, the speed around the circumference of the circle is the circumference divided by the time for one circuit, so 2 pi r over t, the period. So we end up with 2 pi r upon t squared is gm upon r, and then you've just got to do some appropriate manipulations. So 2 pi r squared upon t is 4 pi squared r squared over t squared equals gm upon r. And then I just need to multiply both sides by t squared, divide both sides by gm, multiply both sides by r, and I end up with t squared is 4 pi squared r cubed over gm, which is what I was asked to find. Standard derivation, you are expected to know that, please make sure that you do. But again, the bones of it is that we're doing the usual, equating the centripetal force with the gravitational force. The extra bit we have to throw in is V is 2 pi r upon T. Satellites used in television communication systems are usually placed in geostationary orbits. In your answer, you should use appropriate technical words spelled correctly. State 2 features of geostationary orbit. First of all, they're above the equator, or they're equatorial. And it's that equatorial that needed to be correctly spelt with the pencil mark there. Equatorial or above the equator, they thought was a reasonable way of saying that. The second period is that the period is the same as the Earth's rotation, in other words 24 hours or as a day, or they accepted there that it moves from east to west, from west to east, in other words rotates in the same sense as the Earth. Then calculate the radius of orbit. It's interesting this because they're essentially giving you 3 marks for using an equation that you'd been deriving here, and indeed which they'd given you there. It's not easy because we got T r cubed and the rest of it, and we've got to rearrange. But in essence, we take that equation, we put in the data that we know the mass of the Earth is 6 times 10 to the 24, we know that the period, if you're clever and use your data sheet, you're told that 1 day is 8.64 times 10 to the 4 seconds. Interestingly, that means you essentially had to know that fact there to be able to do this question here. So there's the 8.64 times 10 to the 4 squared. There's the value of g, 4 pi squared, and you had to do a cube root of a number at the end, and you end up with that. So not easy bit of maths, but 3 marks for substituting some numbers into an equation seems relatively generous to me. So that was G484 homework booklet question 23.